Hello again everyone, here we'll be discussing chapter 8.2, law of cosines. In the last video we saw in 8.1, law of sines, which we'll actually be using the same labeling for a triangle. We use capital letters for the angles and their lowercase counterparts for the sides opposite those angles. Now, I would love to prove to you law of cosines like I proved law of sines. It is unfortunately not as straightforward, so instead I'll have a tag somewhere here above that will actually link a proof for that I'll make. Then that'll be fun to check out, but I'm not going to do any examples there, it's just going to be the proof. But here, let me describe what law of cosines really is. In reality, it is actually a generalization of the Pythagorean theorem. And basically, for Pythagorean theorem, we want a squared plus b squared equals c squared, and I'll write that one out first. But I'm going to write it kind of opposite. So I'll write c squared is equal to a squared plus b squared. And this works, but with law of cosines, what it says is that you have to also subtract 2 times the product of those sides times cosine of the angle in between them, which is always going to be the angle opposite the side that's squared on the other side of equality here. And of course, there is a way to subtract these and divide by negative 2ab to get cosine of that angle by itself, which we'll actually kind of need here to solve for the angles, because notice in this example, we're only given the sides. But know that for this generalization of Pythagorean theorem, of course, we need the angle as well. So not only do you need 2 of the unknown sides, but you also need the angle. Which makes sense, because for Pythagorean theorem, we also are given the angle, because in that case, it's a special case of this, where it's a right triangle. And imagine if this C was 90 degrees, cosine of 90 degrees is 0, so you indeed get a squared plus b squared is equal to c squared. So now the only thing I have left to do is just give the other versions where we have different labelings. So one for a squared and one for b squared, of course. So here it'll be b squared plus c squared minus, that's a c, sorry, minus 2 times their product times cosine of the angle between, which is the angle opposite this side here, a. And then here it's going to be a squared c squared minus 2ac times cosine of the angle in between those, which is capital B. Awesome. So this is law of cosines. Very, very, very different from law of sines, although we'll kind of be using it in a very similar fashion in the sense that we will be using it to basically complete a triangle. So we're only going to see a few examples, and then we'll see an actual application of this that involves areas actually, like we saw with 8.1. There's no ambiguous case here, so I don't expect this chapter to be as long as 8.1 was, at least the video that is. But let's take a look. So I want to find these angles. I don't have anything labeled, so let's label this as ABC. So that means we're calling this lowercase a, this lowercase b, and this lowercase c. We don't have any units because it doesn't matter. We only want the angles. We don't care if these are in feet, inches, or meters. That's irrelevant. So let's see if we can set up law of cosines. So I'm going to use, doesn't matter which two you use, I'll use I'm sorry, not A and, but I'll use C and B here. But it doesn't matter. So if we use C and B, that means we want A to be by itself. So we're going to say 14 squared is equal to the sum of the other one squared minus 2 times their product, like that, times cosine of the angle between them. The angle in between them is this A, so this will be solving for cosine of A. Alright, so now I'm just going to off-screen clean this up, solve for cosine of A, and then use inverse cosine to solve for A. Alright, so this is what I got. Of course, I'm just squaring these to get these values, multiplying this to get this 304, combining these to 425, subtracting to the other side to get this negative, dividing by negative 304 to get cosine by itself, and then taking cosine inverse to solve for A using my calculator, and there it is. And let me write this in red here. We got the angle 41.12 degrees. Now let me just say here, I mentioned earlier, there's no ambiguous case for law of cosines like there was for law of sines. And the reasoning is because cosine is different in the second quadrant, unlike sine. Sine is the same in the second quadrant as it is in the first, because the sign is positive in first and second quadrant. But cosine is not. Notice here, we got kind of lucky because we subtracted this to the other side, and we got negative equals negative, divided by negative cancels the negatives. Now, if we subtracted and it so happened that this sum was smaller than this guy, we would have positive, and then dividing by negative would make a negative, actually. And that can possibly happen. Cosine can be negative. That just means we're dealing with an angle that's in the second quadrant. In other words, it'll be an obtuse angle. And in fact, I'll show that here because it looks like the larger of these three sides is 19, and it looks like B is obtuse. So we're going to solve for B. I'm going to erase this, and then we'll write that out right now. Okay, so I've erased all that, and now we're going to follow through the same thing, basically using what we just did as a template. And we want to solve for this angle B. So we're going to say that the side opposite of it, 19 squared, is equal to the sum of the squares of the other ones, minus 2 times their product, times cosine of the angle we're looking for, which is, of course, opposite this side. Perfect. So now, again, off screen, I'm going to just write out all the steps and then explain afterwards. And here we go. Perfect. So we got, of course, basically the same values we got before, just in a different order here. This number is totally different than what we previously had, though. Notice these combine to 260, which is smaller than 361 in this case. So when we subtract 260 to the other side, we get a positive number, kind of like I was talking about earlier. And then dividing, we get cosine's negative, meaning that the angle is actually in the second quadrant, hence obtuse, because cosine's negative in the second quadrant, of course. And using cosine inverse, we get 116.8, which I'll write over here in red. And that's just kind of like what we expected, because it looks like it's obtuse, of course, assuming this is to scale. And really, that's all we need, because once we have two angles, we're done. We can just find the third one by subtracting. So I guess I'm not going to do it off screen. I'll just actually add these together. So let's write it like this. So we get 116.8, 41.12. I'm just going to do this the old-fashioned way, if you will. So I get 0.92 here. This is 157. And then we need, let's see, 30 added to this would be 187, which is too much. So we need 22.08, looks like. 22.08 is the last angle that does it for us. And of course, this is all approximating. If you want to approximate more, then approximate more. But I'm just going 2 decimal places. This is 0.800, so it's legitimately 0.8 if you round to 2. And yeah, so we've completed the triangle by finding all of the angles. Now let me just say, as soon as we find the one of the angles, we don't have to keep using law of cosines. We could actually use law of sines at that point. But be careful that you don't use the ambiguous case. You don't get yourself into the ambiguous case. The thing there is, though, the ambiguous case we saw was SSA. So if you use like these two with this angle that we found, then you possibly get two different scenarios, and it kind of depends. So in reality, it's best to stick with a law of cosines because it's a little more solid, I guess you could say, as far as the math goes, just because the structure of the triangle is already set out if you're given all of the side lengths or most of the side lengths in an angle. But yeah, that's kind of all I'm going to say there. It's really because of the fact that cosine is different in the second quadrant than sine is. So very often we kind of compare these two different laws and see which one's more applicable, but law of cosine is, in my opinion, a little more solid, but it kind of depends. You can't necessarily use law of cosines anywhere you could have used law of sines. They're just a little different, as it turns out. So you can kind of compare, though. You can try it on your own. Once we found one of the sides, maybe you could try to use law of sines and see if you get these two as well. And then if not, try to figure out what you're doing wrong. And notice that you should get these two, of course, because they, of course, add to 180. And also notice that the smallest side corresponds to the smallest angle, largest side corresponds to the largest angle, and the middle one corresponds to the middle intermediate angle. Okay, so I think we're going to do maybe one more example, and then finally we'll move on to that area idea. Okay, so this problem is taken from an application problem. I'm kind of drawing out the details for us, though. So basically we're asked to find the distance from the pitcher's mound to first base, where we're considering this kind of what is known as a baseball diamond, which is the playing field, main playing field for baseball. I don't know too much about baseball, but at least from this shape, it's called a diamond, I know, but it's really just a square if you look at it. All the side lengths are the same and all the angles are the same. So if you consider a diamond just a square on the side, then sure, I guess it's a diamond. But in any event, I kind of digress. Now, the pitcher's mound here is given to be 43 feet from home plate, which is this lower part here, I'll call H. And the way it's organized, it's home, first, second, third. So we want to find the distance from the pitcher's mound, let's call it P for pitcher's mound, to let's call it F for first. So let's call this distance here D for distance. And if you want to use the labeling as ABC like we usually have notated for a triangle, you can do that, that's fine. But here I want to use this. And that's kind of all we have. We also actually have that this angle is given to be 45 degrees because the distance from pitcher's mound to first base is actually the same going the other way to third base. So I made it look like it's a right triangle. It's not necessarily a right triangle, but we'll find out shortly. Actually, if it's above or below, the way I'm drawing it doesn't really look, it's not very obvious as far as which one it is, but we'll find out. Now, this 43, I don't know how accurate that is again, but that's what the problem says. So I'm just going to go based on this, of course. So let's see if we can find this distance here. Notice this is just a triangle where we have these two sides and the angle between them. Also, since it's a square, this is also given to be 60 feet. So if you want, we can kind of just look at this triangle here. And this is basically what we're looking at. So kind of transitioning. This is 60, this is 43, this is unknown. And the angle opposite of the unknown one is given to us, perfect. So that means that, of course, law of cosines is definitely applicable. So we're going to have that the side we want squared is equal to the sum of the squares of the other ones, namely 43 and 60 squared, minus 2 times the product of 43 and 60, like that, times cosine of the angle opposite of the distance d, which is 45. So now it's just calculator time. Again, we can combine these, but to do this, it's hard to kind of do that in my head. 60 squared is 3600, that's fine. 43 squared, I'm going to handle all this off camera like I have been with the other ones. So let's see what that entails. Alright, so I did all the work here and here's what we got. Of course, I kind of showed everything here. Notice that cosine of 45 degrees is a special angle, so we know that's radical 2 over 2. And then simplifying all this, we get about 1800.329. Square rooting gives us 42.43, which is suspiciously close to 43 feet. And as it turns out, I even went a little further on my own and calculated this angle. This angle, according to this, is 90.77 degrees. It's a little larger, actually, so that means this is a little lower. Now, I have a strong feeling, I haven't looked it up or anything, so maybe you can on your own time if you'd like, but I have a strong feeling that the pitcher's mound is actually dead center, but for the purposes of this problem, they're just approximating this angle, or not angle, but this length to be 43. In fact, of course, if they didn't approximate it, it'd be kind of a dumb problem because this would be equal to this. And notice that kind of seems to be the case because they're pretty close, and at the same time, if this was 90, then we have a 45, 45, 90 triangle, and well, then it'd be isosceles, so these would be the same actually. Also, it's a little bit of a digression, but it's not too difficult to see that if it is the case that this pitcher's mound is actually dead center, we can actually find this the side length here pretty simply. It's just 60 divided by radical 2. So if you divide 60 by radical 2, in fact, let me just do that real quickly here in front of us. And let's see what we get. And I get, it's 42.2. Well, it's about 4.3 actually. So it's literally this. But they both be that in this case. In other words, this should be a little lower. This was just approximated for the problem. I believe strongly that's the case because, again, I'm digressing, but it's just, being accurate, I guess. So that's really all for law of cosine. So now again, I want to take a look at another type of area problem like we saw for 8.1. This is a very nice area formula where we don't need an angle like we did in the previous one. Actually, it's a way to find the area of a triangle only given the sides, believe it or not, which is kind of interesting if you think about it, because to find the area of a triangle the traditional way, you need the height, which is not necessarily a side length. If you have all the side lengths, believe it or not, there's a way to do it, and the formula isn't super complicated. I mean, it's kind of complicated, but anyways, I'll stop hyping it up. Let's take a look at that right now. All right, so finally we have what is known as Heron's formula. Heron was actually a Greek mathematician from Alexandria, and he had a lot of ideas involving geometry, and this is one of his biggest and most well-known results, actually, that the area of a triangle of side lanes A, B, and C has an area, the square root of s times s minus a times s minus b times s minus c, where of course a, b, and c again are the side lengths of the triangle. S is the so-called half perimeter, so a plus b plus c all over 2. Now, sometimes this is known as Helios Formula. The translation of his name can kind of be misleading depending on basically the translation in the country you're in, I guess, is really, from what I can tell, what it is. So I know like in England and most of Europe they know it as Helios Formula, but here in the States I guess we say Heron's Formula for whatever reason. But anyways, if you ever see Helios Formula versus Heron's Formula, it's the same guy. It's just the way you say it may be different. Trying to do the Greek accent justice maybe, I'm not sure. But anyways, yeah, so we're just going to do one example based on this. I want to prove this to you. I would really like to do that. It's a little involved, but honestly, it really is an application of law of cosines. And since we know nice formula for area given the angle in between for sine, like we saw in 8.1, 1/2 the product of two sides times the angle in between them, sine of the angle in between them. We can do something similar, but notice here, there's no cosine involved at all. And also there's no height given, which is kind of interesting. So this is something very interesting about triangles, that given their side lengths, you can actually just find the area. And that is actually not true with quadrilaterals. So think of like a square. A square will obviously have a certain area. It'll just be the side length squared. But if you kind of skew things and consider, let's say, this rhombus, which let's say has the same side lengths as this square, you can actually squish this until its area is super, super, super small and almost 0 compared to this area where it's kind of the maximum, you'd say. So with that being said, this idea doesn't really work for all polygons necessarily. Triangles have something kind of special going on where there's a structure. Once you have the sides, the angles are kind of set in place. With quadrilaterals, not so much. But in any event, I'm digressing a bit. Well, like I said though, I would like to prove this for you sometime, so I think I'm going to have a card up here somewhere that will have the proof of this, similar to how I had for the proof of law of cosines. In any event, let's get right to it here. So it's going to be a is equal to the square root of, we need s, and then we need s minus each of these. So s is not going to be too bad. S is literally just the sum of these, so 43 plus 72 plus 53 all divided by 2. Now I'm going to add the odd ones together first. Notice 43 plus 53 is 96. 96 plus 72 is 168, I think. I think that makes sense. Let's see. So that's 96, 90 plus 70 is 60, and then 6 plus, yeah, just making sure. And then if we divide this by 2, we of course get 84, right? So that means inside of this formula here, if I mimic this setup, we have s multiplied by s minus a. So I'm trying to be a little detailed about it. Now I'm just going to call this a, this b, and this c. Notice it really doesn't matter, because since multiplication is commutative, my s minus a may be your s minus c, but since we're multiplying, they're the same result no matter what. So I'm going to get 84 minus 43, 84 minus 53, you get the idea. And then finally 84 minus 72. Awesome. So let's see what happens here. So 80 minus 40 is 40, that's actually going to be 41 actually. This is going to be, let's say it's 31. This is going to be just 12. This is going to be a huge number, which I'll do off screen, and then we'll actually approximate it. So I'm going to say it's equal to the square root of some crazy long number, maybe not super long, but pretty big. And then we're going to square root that and see what this is approximately. Notice this is in inches, so we'll get an answer in inches squared, of course, for area. And then we'll be done with the problem, and then finally with 8.2. All right, so the number was actually quite large. It was 1,281,168, which is a really large number. When we square root this, we get 1131.89 if we round. 1131.89, and let me scoot in that inches squared. And yeah, there we go. That's the area of this triangle. And that's the end for this problem. So it's pretty amazing, again, that we can actually do this. Find the area of a triangle only given its side lengths, believe it or not. So that's the end for that, and as well for 8.2. So I really hope you enjoyed this. And in the next few videos, we'll be discussing more as far as applications of trigonometry goes. And we're going to actually move into something a little different that will still involve some trigonometry, but it's basically going to lead into what are called vectors. It's not the most difficult stuff in the world, I'll kind of agree, but it's just different. So we'll have to take a look at that and see how we can make a connection back with trigonometry. Anyways, I hope you enjoyed this, so I'll see you in the next videos for that. Thanks for watching, and I'll see you then.